Dear students, Assalamu alaikum and welcome to our 18th program on Software Engineering 1 course. In the last program, we talked about what is software testing. We introduced software testing process model that defines the basic activities that are to be carried out in testing a software. Towards the end of the program, we talked about two most commonly used testing methods, generally known as black box and white box testing methods. In this program, we will continue our discussion on testing and introduce some specific white box and black box testing methods. We will discuss basic part testing, equivalence partitioning, and integration testing. In this program, we'll continue our discussion on testing and introduce some specific white box and black box testing methods. We will discuss basic part testing, equivalence partitioning, and integration testing. We'll start with basic part testing technique. Dear students, basic part testing is a white box testing technique that focuses on testing of program structures, program statements, and branches. The technique guarantees that all independent paths within a module have been exercised at least once, and all logical decisions are exercised or executed on their true and their false sides. Before we discuss the basic part testing itself, we introduce a simple notation for representation of control flow of programs called a flow graph. The flow graph depicts the logical control flow using simple notations. A flow graph analysis is concerned with statistically determining the number of different paths by which flow of control can pass through an algorithm. Now, it can be argued that a developer or maintainer must be able to conceptualize the flow of control through an algorithm in order to fully understand its dynamic behavior. Unless such an understanding is available, the developer will not be able to fully predict the dynamic behavior of the program. But before we discuss the basic part testing technique itself, we introduce a simple notation for representation of control flow of a program called a flow graph. The flow graph depicts the logical control flow using simple notations. A flow graph analysis is concerned with statistically determining the number of different paths by which flow of control can pass through an algorithm. Now, it can be argued that a developer or a maintainer must be able to conceptualize the flow of control through an algorithm in order to fully understand its dynamic behavior. Unless such an understanding is available, the developer will not be fully able to predict the dynamic behavior of the software, and thus will not be able to ensure that all possible contingencies are allowed for its design or implementation. Although a flow graph analysis can be made at the design stage, but we are going to show you how to produce the flow graph during the source code analysis. A flow graph consists of a number of nodes shown as circles containing identifying numbers or letters connected by arcs which have arrows indicating the direction in which flow of control will pass. The various notations that are used in constructing these graphs are shown in this diagram. So if it's a sequential statement, it is shown like that. And note one thing, that sequential statement use a single circle. So single circle does not mean a single statement. It might be a block of statements. If then else statement is shown like this one. The first node shows the condition, the C. Now if the condition is true, then we follow that path. That means it should execute state S1. If the condition is false, then we follow the other path and we should execute statement S2. And the last node shows the end of the if statement and remaining flow of the program. A case statement, which is basically a nested if statement, can be shown in a similar way. Here, the node is the condition node where we check the condition. If it is L1, that means the value of C is equal to L1, then we execute statement S1. If the value of C is 2 or the next label, then the next statement, and so on. And the last node here shows the end of the case statement. Now this notation is used to show an if statement without an else part. So we have here the node where we check the condition. Now if the condition is true, then we follow that part and move to that node where we have statement S1 or a block of statements. Otherwise, we go to the end of the if statement. Note here that after executing S1, again we reach to the end of the if statement. The notation for a while loop is shown here. We have a node where we check the condition C. Now if the condition is true, we execute the statement S or a block of statements, and then we go back and check the condition again. Now if the condition is false, we go to the end of the loop. Similarly, the notation for a for loop is shown here. First, we initialize the index variable to its initial value. In this case, it is 1. Next, we check the current value of the index variable with the final value or the last value of the loop. Now, if this condition is true, then we execute the body of the loop, the statement S. We increment the value of the index variable and go back and check the condition again. Now, if this condition is false, then we terminate the loop and we go outside the loop. A do-while loop notation is shown here. In a do-while loop or a do-until loop, we start with the statement. That means statement S1 is executed unconditionally. After execution of the statement, we check the condition C. Now if condition is false, we go back and execute the body of the loop. If the condition is false, we terminate the loop. Here, each circle shows one or more non-branching PDL statements, and each arc shows the direction of the flow. Each edge must terminate on a node as shown in this diagram, that each edge terminates on a node. Of course, these two nodes basically are the some statements which are before it and the statements which are after it, and not shown here. One important thing you should see here, that even if we have a branch, in the case of a while loop, when the condition is false, we know that we end after the S statement. Now, even if there is no statement, we have to include a node which shows the end of the statement. So this node is not a statement, basically it shows the termination of the while loop. Another important thing to note here is that we assumed that all program or algorithm has only simple conditions. However, if the algorithm has compound conditions, that means simple condition combined together with logical operators as and, or, then a separate node is created for each condition. That is, we do not put more than one condition inside a single node. For example, here we have a complex condition: if A or B, then X, else Y. Now, you have to understand what's the meaning of that if statement. It simply says if the condition A or the condition B is true, one or both of them, then we should execute X. Now, if both conditions are false, then we execute Y. So here we have two conditions, A and B, and on our flow graph, they have to be separated and shown in different nodes. Here you can see first we start with condition A. We check the condition A here, the first condition. Now this condition A can be true or it can be false. Now if this condition is true, of course there is no need of checking the second condition B. We simply go and execute statement X. Now if condition A is false, then we should check the second condition, B. So we have a separate node here to check the condition B. Again, the condition B might be true or false. Now if the condition B is true, then again we execute X, otherwise we execute Y. And then this node shows the end of the if statement. And you see here that after executing X, we always go to the end of the if statement. Now you can use a similar kind of technique for other complex notations. Dear students, let's now develop a flow graph from a given program. Here is the program. We have a binary search function. Of course, there is no need of really understanding how it works. We should be more interested here in seeing the loops, the if statements, and the logic of the program. Then, now we separate our loop statements. For example, here is the loop statement. This is a if statement, another if statement. And remember that each condition has to be shown in a separate node. Here all the conditions are simple, so for each condition we will use simple node or a single node. Now once you have identified the conditions and the actions which should be carried out while the condition is true or false, now you simply have to combine the basic notations we just introduced for while, if, and other statements to make up your flow graph. So if this is our function and we want to make the flow graph of that one, then it will look like as shown here. We start with node 1, basically, which is r.font is equal to false, the statement before the while loop. And you can see this structure basically which shows the while loop. Now if the condition in the while loop is false, we go to the end of the loop, and also this is end of the binary search routine. Now this structure clearly shows you that here is a if statement where we check a condition, and we have two branches going out of node 6. If the condition is true and if the condition is false. And node 9 basically shows you the end of the if statement, and also it coincides with the end of the while loop. After node 9, of course, we go back to the top of the loop. Again, we check the condition and carry on. Now, making these type of graphs are quite easy and simple, as long as you know that how to put the conditions and how different notations for if statement, while loop, and other things needs to be combined together to make a complete graph. Dear students, once a flow graph is prepared, we can determine its cyclomatic complexity, which gives us the complexity of the program. If the cyclomatic complexity of your program is higher, that means the logic of that program is complicated. Generally, we try to keep the program logic as simple as possible for the reason of understanding and maintainability. The flow graph we just prepared, the cyclomatic complexity is given by the number of predicate nodes plus 1, where by predicate node we mean the node which contain the conditions, the condition which come after if statement or loop. In our case, there were 3 predicate nodes, So we have number of predicate node 3 plus 1, which is equal to 4. So the cyclomatic complexity of the binary search routine we just saw is 4. Now the cyclomatic complexity also gives us the number of independent paths that should be tested. The independent path is any path through the program that introduces at least one new set of statements or a new condition. In terms of flow graph, an independent path must move along at least one new edge that has not been traversed before the path is defined. The independent paths for our graph are, so this was our flow graph. Now we can easily identify the paths. And remember that we have 4 independent paths, which is equal to the cyclomatic complexity of that graph. So just follow the arrows. So we have path 1, which is node 1, 2. If we move that way, then we reach to node 10. So we get our path number 1. Now path 2, node 1, 2, 3, 4, 5, and then 10. Similarly, part 3 is 1, 2, 3, 4, 6, 7, 9, and back to 2. And after 2, of course, we can follow any path. It can be 2 to 10 or coming back from 2, 3, 4. That doesn't matter now because the rest of the paths have already been traversed. The fourth path is 1, 2, 3, 4, 6, 8, 9, back to 2, and after 2, any path can follow. So, dear students, the intention in white box testing is to ensure that all possible feasible flow of control paths through a subprogram are traversed while the software is under test. If all possible paths through a subprogram are traversed, then all statements in the subprogram will necessarily be executed. The procedure for basic part testing is straightforward. First, we draw a flow graph from the design or code. We then determine the cyclomatic complexity of the flow graph, as we just did. We then determine a basic set of linearly independent paths, and finally, we prepare the test cases. We have already explained the first 3 steps of basic path testing method. That is, how to create a flow graph, how to determine the cyclomatic complexity, and a set of independent paths. Now let us see how do we determine test cases. And remember that by test case we mean the input we need to give to the program and the expected output. So a test case is a set of inputs that can force the execution of one of the paths. Since there are 4 independent paths in our example, we need to create 4 test cases for testing binary search algorithm. We explain how do we determine a test case with an example. Let's say we want to test this path 1, 2, 3, 4, 6, 7, 9, and 2. All you have to do, look at the condition nodes and see that which value you should take which can force the execution of that branch. That means first we have to go from node 1 to 2. Of course, going from node 1 to 2 is non-conditional, so nothing is required there. We'll always move to node 2. Now, node 2 is a predicate node, so we have to see which condition will make the program to go from node 2 to 3. So the transition is from node 2 to 3. Now, this transition will happen only when the value of the bottom is less than value of the top. Then we have to see which values can move our program execution from node 3 to node 4. So, of course, there is no need of it because 3 to 4 is a linear, no condition is required. So any value will automatically take you to the node 4. Next, we have to see how we can go from node 4 to node 6. Now we go to node 4 to node 6 if this condition is false. So we have to select the values of our array in such a way that this condition becomes false so that we can move from node 4 to node 6. And similarly, we have to see which values will force our program to go from node 6 to node 7. Now we have to specify the appropriate input parameters. For example, if the value of key is 10 and our array is 1, 3, and 5, and the value of the arrays that you will input, which will force the execution of each and every path we have specified. Now you can create the test cases for all other paths in a similar manner. Now we will discuss a black box testing method called equivalence partitioning. But before we discuss the method itself, let us remind ourselves of what is black box testing and for what type of errors are generally discovered in black box testing. Now, black box testing is basically used to uncover the specification-based function errors, specification-based component and system behavior errors, specification-based performance errors, user-oriented usage errors, and black box interface errors. As we discussed in the previous program, that in black box testing, we treat our system as a black box. We are not interested in looking at the logic of the program. We only see what inputs should be given to the system and what output we are expecting out of it. But how really those outputs are produced inside the black box, we are not concerned with those details. Therefore, black box testing is testing without knowledge of the internal workings of the item being tested. For example, when black box testing is applied to software engineering, the tester would only know the legal inputs and what the expected output should be, but not how the program actually arrives at those outputs. It is because of this that black box testing can be considered testing with respect to the specification. No other knowledge of program is necessary. One of the black box testing method is equivalence partitioning. In this method, we divide the input domain of a program into classes of data from which test cases can be derived. Test case design for equivalence partitioning is based on an evaluation of equivalence classes for an input domain, where an equivalence class represents a set of valid or invalid states or inputs for the conditions we are going to check. An input condition is a specific numeric value, a range of values, or a set of related values, or a Boolean condition, as shown in this diagram. So in equivalence partitioning, you can see here we have the system we need to test. These are the inputs which have been divided into a set of valid values and a set of invalid values, and of course the output we expect from those values. Let us look at some examples. Assume a system asks for an input number in the range of 100 and 999 inclusive. We can identify 3 equivalence classes of input. For example, our input is 100 to 999, and equivalence classes can be the numbers which are less than 100, the numbers which are between the range, and the numbers which are greater than 999, the upper limit. So we should test our software with some values taken less than 100, some values between that one, and some values greater than the final value. So these are some of the test cases, of course, which have been selected arbitrarily. Let us look at some examples. Assume a system asks for an input number in the range of 100 and 999 inclusive. We can identify 3 equivalence classes of input. For example, Our input is 100 to 999, and equivalence classes can be the numbers which are less than 100, the numbers which are between the range, and the numbers which are greater than 999, the upper limit. So we should test our software with some values taken less than 100, some values between that one, and some values greater than the final value. So these are some of the test cases, of course, which have been selected arbitrarily. As a second example, we have the same value. So our values are from 999 to 1000. Now generally, what we do, what we call the boundary value analysis, we test our software on the lower boundary values and the upper boundary values. For example, if our number starts or the valid range is from 100 to 999, then of course we'll test our software with the value 99, which is just below the lower range and just above the lower range. Similarly, we also test our software with a value which is just above the maximum value the software would expect, and the value which is just below or just less than the maximum value which is a valid input to the software. When you test your software, by giving the value which are close to the lowest value the software would expect from you and the highest value, then generally this is called the boundary value analysis. The reason for testing your software with this value is that it has been established that software generally behaves incorrectly at the boundary values. So it's a better idea to test your software at the boundary values of the valid input. You should also test the system by taking some values for each partition which are not at the boundary as well. Now as a second example, let's see the equivalence classes for our binary search routine we just discussed. Now two obvious partitions are the values of the key is not in the array and the value of the key is in the array. Also, using some other testing guidelines and boundary value analysis, we can define these equivalence classes as shown in these tables. So our input can be an array with single value, in sequence, single value, and the key is not in the sequence, and the rest of the things. And now the input sequence, for example, can be 17, which is a single value, and the key we are searching for is 17, and our expected output is true and 1. True is the value of found, and L is the location of the element. Of course, you can define other values in a similar way so that you test your software for each one of the category at least with one test data. In equivalence partitioning, the basic assumption is that if a test from one partition does not uncover an error, then other members of the same partition cannot identify an error in the code. Dear students, white box testing and black box testing techniques that we discussed can be used to do unit testing. That is, they are applied to each unit or module independently. Once individual modules have been tested, they need to be integrated to create a partial or complete system. But there is no guarantee that when each individual module that have been fully tested are going to work when they are integrated together. Many problems, such as problem with the interfaces, the use of global variable, etc., may arise, making the software behave not as expected and required. Therefore, one needs to test the software while integrating the components. Now, there are two options to integrate the components. What we call the Big Bang approach, in which all the components are integrated together and the software is tested as a whole. And the second strategy, of course, is what we call the incremental construction strategy. There are two approaches for incremental integration testing, generally known as top-down and bottom-up integration. In top-down integration, We start with the top level module, which is basically might be a stub. Then we integrate the modules which are directly called by that module. And we see that how the system works. Then at the next level, we replace the stubs one at a time in a depth first fashion and put the module we want to test. And we carry on like that one. Now, in the case of bottom-up integration, we start with the bottom modules, what we call the worker modules. Now, we take two modules at a time. We integrate them by writing a stub or a module which will make the calls to these modules, and then we see how the system behaves. Then we integrate these two modules incrementally with a third module, and similarly we go to the top level module. Dear students, in today's program we discussed basic part testing, equivalence partitioning, and integration testing. Now, dear students, if you have any comments or suggestions about the program, please do write us on the address given on your TV monitor. And you can also email to us on the email given here. With this, we come to the end of our program. Allah Hafiz.